All right. So, week 6, part 1, we're talking about two examples of F equals ma, and these are sort of classic physics examples. One, we have an Atwood machine, and secondly, block sliding down an inclined plane. So, we'll start with the basics in this lesson. And the idea is that an Atwood machine is two masses attached over a frictionless pulley. And so this is what we're looking at first. So here we have two masses are attached over a frictionless pulley. We assume the string is massless. So we have two masses, and they're going to accelerate. So here we have two masses, and if the masses are the same, we expect no movement. If the masses are very different, we would expect this to move downward and this to move upward, and we would expect them to move quickly. And if the masses were different but not that different, we would expect this to move downward and this to move upward, but slowly, relatively. So this is key for solving the Atwood questions, is you treat the two masses as a system. So there's a mass and there's a mass, and together they move, right, up or down. And so if we treat them as one kind of object, so the difference in their weights, right, force downward, force like the weight due to this one is going to take away from the weight due to this one. So the difference in their weights is the net force accelerating the total mass. So that's key. For example, we are trying to find the direction and rate at which these masses will accelerate. We have a 5 kilogram mass and a 2 kilogram mass, and so gravity pulls downward on this with a force of 19.6 newtons. We call that weight. And gravity pulls downward on this with a force of 49 newtons. We call that weight. So it's obvious that they're going to move in this direction. This is going to move downward. That's going to move upward. They're attached with a string, so they're going to move at the same rate, just opposite directions. And so the difference in these, do you see how gravity pulling downward on this basically takes this much force away from the weight of the 5 kilogram mass? So net force acting on 7 kilograms total is 29.4 newtons, meaning 49 minus 19.6 equals 29.4. So that is net force. F in F equals ma is always net force. Always? Yep, always. And notice how the mass is 7 kilograms. Both are accelerating. And it is this force that goes towards accelerating them. So, dividing gives us this is the magnitude of the acceleration. The big mass would accelerate downward and the small mass would accelerate upward. Let's take a look at page 2, inclined plane. So, in the inclined plane, we're assuming no friction in these examples, and we have a block here. And so if we were to draw a free body diagram, this is it. It's only two forces acting on the object. Gravity weight pulls straight downward, and then because it's on this inclined plane, the plane pushes on the box. Obviously the box doesn't fall through the inclined plane. And we would call this normal force because it is perpendicular to the surface. And so when you look at these two forces, imagine this pulling this way and this pulling this way, sort of in this direction, they tend to cancel out, but there's some left over in that direction. So the reality is that, yes, the block does slide down the inclined plane, and this is what we're interested in, is the result of this force pulling this way and this force pushing this way. What's the resulting force that actually moves the block down the inclined plane? So we can do that by changing our perspective and kind of switching it like this and thinking, all right, we have XY axes, or horizontal, and vertical, or parallel. So these are the terms we use, parallel to the plane, and then this axis would be perpendicular, in other words, normal, perpendicular to plane. So we're going to change our perspective, and what that means is that the weight is actually kind of pulling down and pulling to the side. So we're going to use our SOHCAHTOA skills. Here we go. So we're using our SOHCAHTOA. So we're using our right triangle trig skills to figure out the weight mg, if we're viewing it from this angle, is pulling to the right and is pulling downward. And so we're interested, how much does it pull to the right and how much does it pull downward? So knowing that this is the hypotenuse of this triangle, and that is theta, or 30 degrees in this particular example, this is always the case. After going through SOHCAHTOA, horizontal to the plane or parallel, let's write that in there. Wait, horizontal, yeah. Parallel to plane, and this is the force that slides the block down the plane, and it's going to be this, where that is the angle here. That's a 30 degrees, not a 300. Sorry. And then, perpendicular to plane, this is always the normal force which contributes to friction if it exists. And that is always going to be mg cosine theta. So if the SOHCAHTOA stuff is freaking you out, just memorize that. Here and, let's see, perpendicular and here. Just memorize it, and because it's always the case. So once we have figured that out, so here's our example. We've got a 2 kilogram mass, a 30 degree angle, and it's frictionless, and we're going to find the acceleration. So, SOHCAHTOA, here's the weight. 2 kilogram mass is 19.6 newtons, 2 times 9.8, and we have a 30 degree angle. So this is mg sine theta, and this, the perpendicular component, is mg cos theta. And the reality, so let me explain this in different words. So what this means is that the weight, gravity, pulls to the right with this much and pulls straight into the plane with this much force. So the box obviously isn't levitating up and it's not breaking through the plane. So these, and I'm going to just rotate it like that. So the perpendicular components cancel one another out. This again is a normal force, and we could call this the W sub perp, the perpendicular component, and this, the parallel component of the weight. So that is what goes towards accelerating, speeding the mass up as it slides down the inclined plane. So in this example, our net force is just 9.8 newtons, and that's equal to mass times acceleration. So we get 4.9 meters per second down the inclined plane. Next lecture, we will discuss what happens when there's friction. And it's a little more complicated, but we can do it.